I wanted to quickly review what we did in our most recent video. Okay, so the basis behind section 5.1 is that you learn what a Riemann sum is and what it means to evaluate a Riemann sum using a left-hand Riemann sum or a right-hand or a midpoint. At the end of the chapter, we're going to even talk about trapezoidal Riemann sums. So keep in mind the three goals: approximating the area between a curve and a horizontal axis, interpreting what it means, and then understanding if you've had an overestimate or an underestimate using your approximation. Okay, we talked about speed, total distance, distance being equal to the area when you graph the velocity. And then what we did here in this mainly our first example of approximating area, taking the curve y equals x squared plus 1 on the interval from 0 to 2, we approximated the area under the curve using a left-hand Riemann sum, and we used two subintervals. So let's clean it up a little bit. Okay, using a left, that's what we just did. Okay, using a left Riemann sum, find the approximate area under the curve y equals, and we can approximate the area under any curve. In the most recent example, we approximated the area under the curve from x equals 0 to x equals 2 with two subintervals. Okay, so what we're going to do now is we're going to evaluate we're going to use a right Riemann sum, and I'm going to show you how a right Riemann sum is different than a left Riemann sum. So this should make it a little bit more clear. This is the type of question you're going to see, and that's helpful too, I think, when you see, oh, what does the question actually look like? So the way you set it up is the exact same way we set it up in the last problem. You make your interval from 0 to 2. You draw the curve y equals x squared plus 1. Now using a right Riemann sum with two subintervals, okay, the first thing we're going to do in figuring out how to approximate this area is we notice that we've got 1, 2. Our entire interval is from 0 to 2, and when you break that down into two subintervals, unless you're told otherwise, you're just going to make sure that the subintervals have the same width. Okay, so each of these subintervals is what you see right here. These are the subintervals. Each of them has a width of 1. Okay, and so if we back all that stuff out, clean it up a little bit, on the first subinterval, which would be from 0 to 1, okay, first subinterval, you just draw the bottom of the rectangle. Okay, remember what we're doing here. We're doing a right Riemann sum, so we take the right end. Okay, this is the right side of the interval. Okay, from that spot right there, you move up, straight up until you hit the curve. Okay, what you've just done is you've just drawn two sides of your rectangle. Now you just complete your rectangle. Okay, there's your first rectangle. Then you take your second subinterval and you draw the base of the rectangle. There's your second subinterval. Again, it has a width of 1. And then from the right hand side, again, from the right hand side, you go up, straight up, until you hit the curve. Okay, and then you complete your rectangle. You have two sides of the rectangle, you just complete the rectangle. So now we can see we have two rectangles because we have two subintervals. Okay, so then we just have to find the area. So let's see here. I'm going to find the area. I'm going to introduce this notation one more time. Okay, this notation, that's the integral from 0 to 2 of our function x squared plus 1 with respect to x, okay, is approximately equal to. So now you're learning, alright, well, what's the connection between the integral and our approximation? Well, we're going to approximate the integral using a right-hand Riemann sum, okay, and one more thing I'd like to point out, this guy right here, you will learn, you'll learn it for a little while, but you'll learn that this is actually the exact area under the curve. Now, keep in mind, it's exact area under the curve because the curve x squared plus 1 is greater than or equal to 0 on the entire interval. So, as I said before, we'll talk about situations in which the function is actually underneath the x-axis on within that interval. All right. So then all we have to do is come up with the area of this first rectangle. Okay. Well, the area of the first rectangle, again, the length of the base is 1, and the height here now depends on 1 being the input, and 1 being the input. The output would be 1 squared plus 1, and 1 squared plus 1 is 2. So the area of that particular rectangle right there is 2. Okay, so I just put a 2 inside the rectangle, and I'll put 2 right here, plus. Now we need the area of this rectangle. Okay, that's the second rectangle. And again, the length of the base here is 1, length of the subinterval is 1, and then the height of the rectangle would be dependent upon the x value of 2, because 2 is on the right hand side of that rectangle. Okay, so the height depends on the right hand side. And then again, the height is x squared plus 1, so if x is 2 here, we have 2 squared plus 1, and we get 5. And so therefore, 5 times 1 is the area of that rectangle. And so we know that the integral from 0 to 2 of x squared plus 1 dx, okay, the approximate area under the curve using a right Riemann sum is 2 plus 5 equaling 7. And that is our right, using right Riemann sums, that's the approximate area under the curve from x equals 0 to x equals 2 with 2 subintervals. Okay, so given that, on the next slide I'm going to have you guys do one, and then I'll show you, I'll work through the solution after you try it on your own. Excuse me, and then we'll go from there. Sorry, I take it back. I forgot one last thing. We had goal number 1, which was to find the approximate area, and then goal number 2 was what in the world were we finding, and that's this guy right here, the exact area under the curve. We're approximating the exact area under the curve. But goal number 3 I forgot to talk about, and that's, was it an overestimate or was it an underestimate? In other words, does 7, the number 7 here, does that represent a value for this integral here that is too high, or is that approximation too low? Well, we can hopefully clearly see that the approximation is too high. Okay, and we'll talk later about how we would know if it's not as clear as what we're seeing here. Okay, so that approximation is too high, and the other one, if we back up here, that approximation was too low. Okay, so I will now give you a blank slide, and I'll get you started here. So I'm going to pause, and so I can write it down. Okay, so here's the problem I'd like you to do. Using a left Riemann sum, find the approximate area under the curve y equals x squared from x equals 1 to x equals 3 with 2 subintervals. In other words, approximate the integral from 1 to 3 of y equals x squared dx. Okay, that's what you're going to be approximating. You're using 2 subintervals. Pause the video and then play it when you're done. So you're approximating the area under the curve from x equals 1 to x equals 3 using 2 subintervals and a left Riemann sum, meaning that the left side of each subinterval is going to hit up from the left side of each subinterval. You're going to find the height of each rectangle. So our first subinterval is from 1 to 2, and the left hand side of this subinterval from 1 to 2 is 1, and you go up till you hit the curve, and so you have a height of 1 and a width of 1, and so you get an area of 1 for that rectangle. And then the second rectangle, you go up from 2, so you go up from 2 all the way till you hit the curve, Okay, draw the base right there between 2 and 3, up from 2, and then you finish your rectangle. See how the top left corner is the one that hits the curve. Oh, let me do that in a different color. Okay, top left corner of the rectangle. Okay, that's the part of the rectangle that hits the curve in a left Riemann sum. So if it's a left Riemann sum, then the top left corner hits the curve. By the way, up from 2, we know y equals x squared, and so we know that the height of that rectangle is 4, so 2 squared is 4. 4 times 1 is 4. So our approximate area, approximating this integral, that integral has an approximate value of 1 plus 4, which is 5. And that's our approximate area under the curve, using a left Riemann sum.